there, everybody. This is your TA Christian. I'm going to be walking through this problem here on grammars and trees generated by grammars. So in this problem, we have a grammar G2, and we have a set of rules here where S is the starting symbol and the terminal symbols are A and B. And we would like to show that any tree generated by G2 has an equal number of A nodes and B nodes. So before diving into some of the actual proof details, let's maybe draw a couple pictures, get familiar with base cases, and maybe start thinking about what we're going to need to show for the inductive cases. So for the base cases, let's just try to make, say, the smallest trees that we can. So one thing we see here is that if we're at symbol S, there's no terminal symbols on their own here, but there are symbols where we can have one terminal symbol and then go down to these other rules, which themselves have terminal situations. So let's maybe start with um, this option here, and we're going to try to generate a short tree using that. So let's make a vertex. So S here, and then we'll have B as one of the leaves here, A. And now, since A can actually terminate, we're going to create a vertex that will be a leaf. This will be A. And so what we have here is one of the base case trees that can be generated, basically, which has a height of 2. And so now let's try again. So we have S. This is going to follow similarly. But what's going to happen is we're going to choose this rule here instead. So we're going to have A, we're going to have B, and then B has a child that can terminate of B, lowercase b here. So both of these correspond to base case trees that have a height of 2. So we can't have any trees that have a height less than 2 in this problem. And as we can see in this base case, we do have the same number of A and B symbols in both. So now what happens if, say, we look at this? Well, let's just generate this a little bit. Okay, so S is our root, but now let's think a little bit here. We're going to have two children that are S. Oops. So let's look at this a little bit here. So we're going to have two children that are S. And by the structure, they're going to have some trees associated with each of them. They could be different heights. These children's subtrees could be different heights. But what we know is if we were to say, claim that this overall tree has height h, then one of these trees down here must have height h minus 1. One of them must. But what we know for sure is that both of them have height at most h minus 1. And so if we were thinking about this, say, inductively, where, say, we were like, oh, all trees generated by the grammar G2 have equal number of A and B nodes, well, what that tells us is in each of these subtrees here, the number of A here is equal to the number of B, and say the number of A here is equal to the number of B. So this we know for sure, and in this particular case, there's no other A or B symbols since the children of our root are just S and S. So if the number of A's and B's are equal in both subtrees, then obviously if we add them together, the number of A's and B's should be equal for the whole tree. Okay, so that's one sort of case to think about. Okay, now is there anything else? Yeah, there's some more interesting ones. So we have by these rules cases like these. Now, technically, like this right here. So technically, um, we really only need to consider one because you can do these symmetrically. So let's take a look. So let's draw this tree. So S, and we're going to go say B and A as children. Oops. Okay, so let's just draw this. So B, A, and now A, what we're going to do is we're going to use this situation here. Okay, so then in that case we have A and S as the children, and then S is some subtree, right? Okay, so by an inductive hypothesis, if we wanted to approach it that way, what we know is that the number of A here is equal to the number of B, right? And if we also look at the structure of how this is, we have one B and one A here. So the number of A's and B's then for this whole tree are going to be equal. And just as a fine point, why can we apply the inductive hypothesis? Well, we know that if this overall height is h, then, and this right here is only a leaf, that tells us that this must have height h minus 1, and then this tells us that this height must be h minus 2 technically. But the point is really just to say that we know that this subtree has height strictly less than h. That's what matters more than anything here. And so since we see that, we can apply an inductive hypothesis and we can get our result. So I guess from here, it's about time that we try to work out the formal proof. So I'm going to clear all of these things here. So we're going to start this by choosing some integer k that's at least 2. Okay, so what we're going to do from here is we're going to make the following assumption. We're going to say for all trees generated by G2 with height strictly less than k, they have an equal number of A and B nodes. Okay, so we're going to have this as our assumption for the problem. And so consider an arbitrary tree, say T prime, with height k that is generated by G2. So we have two cases to worry about here based on parameter k. So if k is equal to 2, the two possible trees T prime can be are, so it's what we drew earlier, and in both cases there are an equal number of A's and B's. Okay, so that's one case. So we're covered there. So now we have another case to worry about, which is if k is larger than 2. Maybe we'll just change the wording and we'll say, suppose k is larger than 2. Okay, so what can we get here? So we have a few cases, subcases to consider here. So let R equal S, be the root of t prime. Suppose that the children of R are S and S. So since t prime has height k, the two subtrees rooted at the children have height strictly less than k. So by the inductive hypothesis, the number of A's and B's in each subtree are the same. So thus, t prime has the same number of A's and B's. Okay, so suppose R has children A and B. Since k is larger than 2, this implies that B must have children let's see, must have children B and S. Now, before I keep going, why must this be true? Well, it's because if B had child that's just B, which is this case here, this would correspond to one of these trees. In fact, it would be this one right here. And that tree has a height of exactly 2, but t prime in our case has to have height larger than 2. So it cannot have that as B cannot just have the child of B, lowercase b. So we know this must be true. Um, okay, so the subtree rooted at grandchild S has height less than k. So by the inductive hypothesis, we know this subtree has an equal number of A's and B's. Now, since we have child here of A and a grandchild of B, and then whatever, A's and B's that live inside of the subtree rooted at S, this tells us that we have the same numbers of A and B. And this is because have only one extra A and B outside of the subtree rooted at S. Okay. All right, so what other case do we have? Suppose R has children B and A. Well, this is handled the same way. So we're just gonna be saying can be done symmetrically, basically. So this follows by similar uh, discussion as the above case. Okay, and so that covers all of our cases because S only has these three things that can happen. And so, I guess sort of conclusion. This basically is enough, but since K was chosen arbitrarily, this implies that any tree generated by G2 must have an equal number of A's and B's. And that is it. Thanks for watching and have a good one.